Welcome to The Explainer. Today, we're diving into something really cool. How science figures out what actually causes something versus what's just kind of hanging around it. It's all about separating the clues from the real cause. Okay, let's kick things off with a real-world example. A study looked at teens and found this crazy strong link, a correlation of -0.85 between nighttime phone use and how much they sleep. Whoa. That basically means the more time they spend on their phone, the way less sleep they get. So they're definitely connected. But how? So is the phone the bad guy here, literally stealing away their sleep? Or could it be the other way around? Maybe teens who are already having trouble sleeping because of stress, anxiety, whatever, are just grabbing their phones to kill time. See the problem? A correlation just tells you that two things are related, that they're moving together. It doesn't tell you which one is calling the shots. So that's the big question, right? How do we get past what's related and get to the bottom of what's the actual cause? Well, for that, scientists have a special tool up their sleeve. It's called the experimental method. When you break it down, it's really just a carefully controlled test. And you know what? Let's build one ourselves right now to answer a question we've all wondered about. Does studying more actually cause you to get better test scores?
Okay, let's get into the nitty-gritty. Every single experiment, no matter how complicated it seems, is built on two key things: the independent variable and the dependent variable.
Think of it this way. You've always got a cause and an effect. The cause is the thing that the researcher is actively messing with, and the effect is, well, it's the result you measure to see what happened. Let's dig into that cause part first. That cause is what we call the independent variable, or IV for short. It's the one thing that we as the researchers are in charge of. We change it on purpose. So in our little study experiment, the IV is the amount of study time. We might tell one group to study for just 1 hour and another group to study for 4 hours. See, we're controlling it. All right, so if we're changing the study time, what are we hoping to see a change in? What are we measuring? That's our dependent variable, the DV. Its value depends on what we did with the independent variable. For our experiment, that's super simple. It's the scores on the test. But hold on, it's never that easy, right? Real life is messy, and experiments can get messy too if we're not careful. We've got to be on the lookout for these little saboteurs called confounding variables. They're these hidden factors that can completely wreck our results. Think about it. What if some students are just naturally brilliant at the subject already? Or what if one group is trying to study in a loud, crowded coffee shop, while the other is in a perfectly silent library? Any of those things could totally change the test scores, and it would have nothing to do with how long they studied. Okay, so with all these potential pitfalls, how on earth do we design a fair test? Well, it's all about isolating that one true cause. First things first, you split your participants into two teams. You've got the experimental group. These are the folks who get the special treatment, like our 4-hour study plan. But how do we know if that plan is any good? We need something to compare it to. And that's where the control group comes in. They just do what they'd normally do, which gives us a perfect baseline. Now, here's the absolute most critical part. How do you decide who goes on which team? You can't let people pick, that's for sure. The secret sauce is random assignment. We're talking flipping a coin, drawing names out of a hat, whatever it takes. The goal is to make sure every single person has an exactly equal chance of ending up in either group. And here's the cool part. When you do that, it's like magic. All those pesky confounding variables we talked about, motivation, prior knowledge, you name it, they tend to just balance themselves out across both groups. It is the absolute key to a fair fight. Okay, so even if our groups are perfectly balanced, there's another hugely powerful force we have to deal with: the human brain. And this brings us to the famous placebo effect. It's this wild idea that just believing you're getting a special treatment can actually make a difference. In our study, for example, if the students think they're getting some revolutionary new study guide, they might just feel more confident. And that boost in confidence alone could bump up their scores. And hey, it's not just the people in the study. We, researchers, are human too. We have biases. If I'm secretly hoping my new study guide is a game changer, I might, without even realizing it, be a little more encouraging or give tiny hints to that group. That's called experimenter bias, and it can totally poison the well without me even knowing I'm doing it. So what's the solution? You basically have to keep people in the dark. In what's called a single-blind study, the participants have no idea which group they're in. That's pretty good. But the real gold standard, the best of the best, is a double-blind study. In this case, nobody knows who's in which group. not the participants, and not the researchers running the test. Not until all the data is in. This is, hands down, the best way to protect against both the placebo effect and our own biases.
All right, we've run our perfect double-blind experiment. The results are in, and they look amazing. We've done it. Or have we? Before we can start telling everyone about our amazing findings, there's one last massive hurdle we have to clear.
Here's the deal. Our results are only as good as the people who were in our study. That group of people is called our sample. And those results only mean something if our sample actually looks like the much bigger group we want our findings to apply to, what we call the population. So let's say only the super keen straight-A students signed up for our study. That's a classic case of sample bias. Can we really claim our study guide works for all students if we only tested it on the top performers? Yeah, probably not. What you're shooting for is a representative sample. It needs to be like a mini version of the real world, with all the diversity in age, background, skill level, and so on. The opposite of that is what's called a convenience sample. That's where I just, grab the students in my first period class because they're, well, convenient. It's easy, for sure, but there's no way that one classroom is going to represent all students everywhere. Ultimately, this whole thing boils down to a single critical word: generalizability. It's basically asking, how confident are we that what we found in our little experiment can be generalized to the larger population? If you don't have a good representative sample, your generalizability is going to be low, and your results, honestly, might be pretty much useless out in the real world.
So there you have it. You now have the basic toolkit of a research scientist. You know how to tell the difference between these two things are related and this one thing causes the other. The big takeaway here is that the next time you see some splashy headline about a brand new study, I want you to take a breath, pause, and ask yourself one very simple but very powerful question.
Just ask that, seriously, because if the group of people in that study was biased, if they don't really represent the people you're thinking about, then the results might not mean what the headline says they mean at all. It's the first and maybe the most important step you can take to really understand the science you see every day.